Welcome to the next video in the Systems Programming video series. We are currently picking up where we left off, which was to examine this very small C program. And that makes calls to functions which are back here, but we've talked about this already. It generates this assembly when we make a call to objdump. And we're now going to trace through the assembly code that it generates. So starting here, we've already said that these two lines are both boilerplate that happen with just about any function call, and therefore we're not going to parse them too quickly, too carefully, but we will just say that the push pushes the base pointer, the old base pointer, onto the stack. So the old base pointer was 830. That gets pushed onto the stack, and the stack increments so that it is now pointing here. That's the push call. Down here with the move call, we take the stack pointer address and copy it into the base pointer address so that now both the stack pointer and the base pointer are pointing here. And you can see how these updates correspond to how the registers get updated, right? The stack pointer increments because any call to push always increments the stack pointer, and the instruction pointer always increments on every step. And here, the base pointer got updated because something got moved into the base pointer, and the instruction pointer increments. So now getting into the first possibly interesting step, we are now going to subtract the constant number, and keep in mind this is written in hex, so 10 is actually code for 16 in hex. And so we are going to subtract 16, meaning that we move up from, that's not at all what I wanted to do. We are moving up from the old stack position, right? Because we are subtracting off of the stack pointer. So we're moving the stack pointer and we're giving it space enough so that it now points up here, right? And of course, right, you can kind of just do simple arithmetic to see that even in hex, D40 subtracting 10 gets you D30. So that explains the new address of the stack pointer, which you see basically there and there. And what we are doing is we are basically moving over this base pointer address so that we don't write over it. We want to preserve that base pointer address so that we can get back to where we came from later in the run of the program. But moreover, we're moving an additional 8 bytes so that we have room for another 64 bits, that is to say 8 bytes, for this integer x that we are going to be working with, right? And keep in mind, let's flip back to the C code and see that this is effectively in correspondence with declaring the integer x, right? That we want to reserve memory for this variable x, which stores an integer, and so we're basically making, space enough for this integer x. So, effectively, we're trying to reserve this region of memory for the variable x, right? The assembly doesn't know that, so to speak, but you and I understand that that's how the C code is in correspondence with the assembly code. Okay, next, we call Q, right? And we talked previously about what that means. It effectively just means that we are doing stuff to the instruction pointer. You can see that here, right? That we are going to give it the instruction pointer that is the instruction that the assign function begins with, right? And actually, it's probably worth going back to the assign assembly code. Where did we get that objdump here? And assign starts with 40526, and so that is why in this abbreviate, right, because all of these addresses here are abbreviated for readability, but that's why this is 526, is because we are giving it the instructions which begin the assign function. We also tell it that it is the assign function. And so, as we said, right, the call Q is going to update the stack pointer. That's, you can go back and see what we said about the call Q assembly command, but it will update the stack pointer to get things ready for adding a new stack frame. And it will also hand over the instruction pointer to the instructions that are needed for the callee function, which in this case is assign. So notice that the stack pointer used to be at 38, and now it is at 28. Or sorry, that's not correct. It used to be at 30, and now it is at 28. Oh yeah, here, nice. We don't have to flip back to look at what this is equivalent to. We push the instruction pointer, so the instruction pointer goes here. That's the old instruction pointer, so that is, or I guess old, maybe that's not the right word, but the one that corresponds to the caller, right? So here main is the caller function, the one who is doing the calling. And so its next instruction pointer is what gets pushed to the top of the stack. This is part of just like what you always want to do when you call a function, right, in assembly that corresponds to these kinds of moves. And so, right, so we push the instruction pointer onto the stack, and then we move the new instruction address into the instruction pointer. So basically we're just getting ready to run the instructions of the callee. So that's what this call queue does. Now that we have done this to call queue, on the next page, you're going to see that we don't want to be looking at this assembly anymore because we now need the assembly for the assign function. So let's move over to that. Okay, now here's the assembly for assign. What do we do with assign? Boilerplate for any function call. So the push and the move, just update the stack so that the stack information is ready for when we, for us to perform these functions, and also keeping track of the old base pointer. I guess let's, by the way, remark that, we said it a little while ago, but now it becomes relevant that D40 was the old base pointer. That's what we are writing when we push, so that we can remember how to get back to the old stack, the base pointer. Anyway. So push is boilerplate, we've already talked about that. Move is boilerplate, we've talked about that. I'm just gonna skim over these fast now because we've kind of talked about them twice. And we get to the next interesting thing that we could possibly do. And that is here that we are going to move the value, the hex value to 8, which, if we wanted to compute that, that would be, and it's a constant value. So it's like literally this value that is like getting moved over there. So anyway, we are going, what is this? This is 2 times 16 plus 8, which is what, 3240. That's in decimal, that would be the number 40. And who knows, like, do we need to know that? Probably not, but let's just have it anyway. And so we move this into this address, which is the new base pointer. By the way, at this moment in time, where is the base pointer? Well, since we just did a push and a move, then that means that both the stack pointer and the base pointer are here. And so what this is saying is that we're going to take this number and put it into the address of the base pointer, but up, that is to say subtracted by 4 in hex, which is just 4 in decimal as well. Anyway, so the point is that we are going to go, I think the stack pointer and the base pointer, this is after the call. So anyway, the stack pointer and the base pointer are both here, and we are going to go 4 addresses above that place. So this is 4 addresses above. That's the -4, getting us from this address to that address. And into that address, we write the number 40, or in hex, 28. So that's what this move is doing. Now, what does that correspond to in the function assign? So let's go back to the assign function so that we can see why we might be doing that. Well, what does the assign function do? It takes the number 40 and it puts it into the variable y. So what we're effectively doing is allocating space for the variable y at this address, which that's like the -4, like we're going up to that address, and we will use it to store this integer. And in that location, we're going to store the number 40, and that is, as we said, the same as the hex value that we have been talking about. Yeah, where am I supposed to be at this point? Oh yeah, here, okay. Right, so we have, in a sense, this is like the y variable getting assigned the value 40. Okay, moving on. Next thing we do is we take that value that was put into the variable and we move it into the return register, right? Remember, EAX was, or well, RAX is the return register. EAX is the portion of it that we would need for an integer, right? It's 32 bits, which is all you need for all you would need for a 4-byte integer, right? Integers take up 4 bytes, so that's why we're using E, which takes up only half of the 8-byte register. So effectively what we seem to be doing is we're basically priming this value to become the return value, which if you recall what the C code said, right, we just assign Y the value 40 and then return Y. So this is like basically corresponding to the return line. And then everything after that, we've talked about these steps before in previous videos. These are the steps that you tend to do when you are getting at, like handing control back over to the callee, which in this case was the main function. So so I'm going to kind of go quickly over the next two steps. That like this step does some stuff to the registers in the memory. In fact, maybe not even to the memory, but the point is it does stuff that we've already described in earlier videos here, and the basic purpose of them is to hand control back over to the callee, which in this case is main. So we're just going to breeze right over those things. And now we're here looking again at main, right? Control has now been handed back over to main because we saved that instruction pointer to hold this. Then this is the next line that executes, right? So how does the computer know to come back to this place? It was stored in the stack. I think maybe we no longer see it because we popped it and wrote over it or something like that. Is it still here? Yeah, here. So right, like that 55F, which got loaded into the instruction pointer, is why in this moment, we are currently evaluating or running command at 55F. Okay, what do we do here? Very similar story to last time. This is a call. We give it the instruction for the first instruction in adder, the address for the first instruction in adder, and we're calling on the adder function. So the next thing we're going to look at is the adder function's assembly code. So what does that do? We push, we move. Those do things to the stack, which we've now described a couple of times, so we won't go into detail. What's the first interesting thing that we do? Recall that here it's probably worth looking at the original C code for the adder function, where I believe we just jump straight into a return. So what is that? Is that here? No. So here's the adder function, right? And that's right. We declare a variable and then return without ever initializing it. And a lot of the point of this current exercise is to understand why it seems like this A absorbs the value 40 left over from the earlier function call. So let's go back and see why that would be. Yeah, we are basically taking the value that is stored at the base pointer. So what's the base pointer at this precise moment? It should be this right here. That is both the stack pointer and the base pointer at this moment. And we're going to look 4 addresses above, keeping in mind that this is memory that we wrote to, but then we abandoned because we left the function call, but it's still left over there, right? When you end a function call, it doesn't perform any cleanup. It doesn't zero that value out or anything like that. So the old value is left hanging there. And like when you say that you want to return this, it's just going to go look into the memory allocated for the variable A, and it allocated this memory for A, or in fact, I guess this is the memory allocation. Is it? No, I guess this is just saying that we're gonna be returning, right? That like the value located here is going to be the return value because we're making the return register look there. And then the next thing that we do is we add 2 into the return register, right? So that's this, add 2 into the return register. So you can see that the return register got, sort of declared to be this, and we're going to add 2 into, or sorry, is that right? Sorry, yeah, I should not be pointing there. I should be pointing here, where 2 gets added into the return register. And then we return, right? We do the things that you do when you return a function. Anyway, long story short, this is why we get 42, right? This is the code for 42, and this explains the behavior of the C program. Fundamentally, it's all due to the fact that we previously, with a previous call to the function, put the value 40 here, and then on the next function call, we just sort of allocate memory for a variable, which basically just makes the computer understand that variable is going to be at this address in memory. But then we don't initialize it with anything, meaning that the old value is still sitting there. And so basically at that moment, the value in the variable a is 40, and then we return 40 plus 2, which is 42. So, okay. I think from here, it makes like all the rest of the code, right? You do this boilerplate for exiting a function call, and then once you have exited the function call, you're doing the last few things that happen in the main function. And so I think like this right here is taking the old return value, right? The return value from the function we just called, and moving it into the space allocated for the integer x, because remember this, as we were describing it at the beginning of this video, was this from the perspective, from the stack frame of the caller, the main function. That was the address of the variable x. We allocated this for x, and so that value is getting updated with the return value from the previous function, which was 2a, right? The hex code for 42. Anyway, so that's what this is, and then this is going to move that value into the return register. I'm not entirely sure why that would be. Does the book give an explanation for places it back into REX? So yeah, I don't know that we, why do we put that value in EAX? I'm not sure. It might just be that like the last value you assign always just goes into EAX. I don't know. Anyway, I don't think it's terribly important to know exactly what's going on there. But okay, so EAX, the address of EAX goes to ESI. Now, what is ESI? Let's see. Yeah, I guess the move instruction address copies the value EAX to register ESI, which is the 32-bit component register associated with RSI, typically stores the second parameter to a function. So why would it do that? I mean, especially in this setting. Oh, maybe this is so that really for the print call, right? Because I think we call the print function or printf, which is going to take a formatted string, and then the value that is supposed to go to the formatted strings, indicating locations. Anyway, so I guess this is to get ready for the call to printf, so that the value of x is there ready for that call to the function, so that it's in the second argument of the function. Then we move this constant, which presumably is the hex code for the format string that we use, into EDI, which I would imagine, right, that's the register for the first argument of a function. Right, so it is the base address of the string right here. And this is in code segment memory, I guess is important to say, is that like we, in order to do this, we are in fact going, not straight from the assembly, not straight from, heap memory or anything like that, but rather we are going back to the code segment memory to look up, right, to get this string. Anyway. Then we move the value 0 into the return register. Can't honestly say that I know why that is. The book doesn't explain. Probably we don't need to know right now. Then we make the call to the print function. That is presumably quite complicated, and we do not want to be looking at walking through what happens when you make a call to the print function. And then now this moves 0 into the return register makes total sense because that corresponds to the line of the C code saying that the main function returns 0. And then we do boilerplate stuff to exit the main function. And I think that concludes the walkthrough. Is there anything interesting? I think that's it. So there we have it, finally finished with the walkthrough.